Everybody, let's get started again. I'd like to introduce our next speaker, Nicolai Lynnerup. He spent a good portion of his career investigating the very topics of this workshop in two very different settings. In his current role as Research and Innovation Engineer at Universal Robotics, he is exploring machine learning applied to computer vision and control algorithms, working to discover out how to apply the research into their product. Prior to this, Nicolai worked at the Danish Technological Institute, which is an R&D shop focused on pushing forward the state of art product, not research. Nicolai put his teeth on pure research while at the Danish
University of Southern Denmark.
Thank you. And sorry, I actually had it in Danish and I forgot how to pronounce it. Yes. Where he also earned his PhD. Anyway, thank you very much, and looking forward to this talk.
Thank you, James. Yeah, so I'm Nicolai, and you didn't butcher my name all the way, so it was good. It was good. Yeah, and as James said, I'm a research and innovation engineer at UR, and I've been here with this company for close to 6 months now. And before that, then I would have spent 5 years approximately working in the intersection between academia and industry. So the agenda for today, for my talk, is I would just briefly go into who Universal Robotics is, then reproducibility in real-world robotic learning, and then how we do innovation at UR. So those of you who don't know us, we build collaborative robots, and our vision is that we want to create a world where people work with robots and not like robots. So we want to be able to work healthily close to the robotic systems. We're a relatively new company compared to other robotic brands. We started out in 2005 at the University of Southern Denmark, where a group of students there started to build these prototypes. And a lot has happened since. I will not go into the details of that. Some numbers during this relatively short time period here, we have over 800 employees based around the world. We have headquarters both here in the US and Boston, and we also have that in Lynnerup. We have sold over 50,000 robots, and we have hold a pretty substantial amount of the market share, which we try to hold. As I said, we're a global company. Headquarters in Denmark, Lynnerup, and in Boston, in the US, and then we have a lot of global offices. Good. So, what I spent close to 4 years about doing in my PhD is this reproducibility for real-world robot work, specifically for reinforcement. I would like to start out by a quote from Joel, who said that reproducibility is a minimum necessary condition for scientific finding to be believable and informative. So thinking about science and why we all entered science, why we work in academia, we want to progress the knowledge, we want to limit the fears of the unknown, we want to make the world a better place to live. Sadly, within reinforcement learning, especially for real-world robot learning, we have had a lot of issues, and still have a lot of issues in reproducibility. So how can we actually overcome these issues? What is reproducibility? What does it mean? If we take a man with the awesome hair, Albert Einstein, then he said that insanity is doing the same thing over and over again and expecting different results. And well, that's basically what's happened in a lot of research within machine learning. Jokes aside, even the terminology about reproducibility is a very discussed topic, and that's a shame. We used the first part of my PhD to actually dive into the literature and come up with the definition of what is this. So we have a common ground, so we don't have to argue about what does the different So we have the repeatability, we have the same team doing the same experiments and setup, conducting the same experiments. You run different trials over and over again to validate your results. Then we have the reproducibility, where you have a different team trying to validate the results for other groups, right? But they're using the same experiments and setup. Obviously, this is not a black and white scale, especially for robotics. Then how do you define which is the exact same experiments and setup? Because you cannot use the exact same robot. You have wear and tear on the robot. You cannot ship a robot from the US to China if you want a group there to actually work on. That's just infeasible. So for our definition, we have mainly that we use the same code base, we use the same libraries, we use to conduct those trials, and then on similar hardware. Then we have the replicability, where you have a different team using a different experimental setup, and that's sadly the thing that I used the most of my PhD doing, because it was so hard to get people's code to run. It was hard to make different robot brands do what you actually want them to do. Yeah, so that was the definitions of those terms here. But what is the needs of the industry? When we think about what is it that we want in industry from the academic world? So first of all, we want the technology to be accessible. Obviously, if you cannot access the technology, then don't use it. Then we need guarantees about how it works, and we need plug-and-play code. Most companies do not have the time to spend on integrating different parts together. They want smart cameras that they can plug into a robot and use that with this. What we see, especially for the accessibility, which also relates to this reproducibility a lot, is that the technology is very elegant, which means that, some of the other guys previously also mentioned, that in research, then many times it's shown that it works once. That's great, but that's like no hands research. It works once. I'm not sure if it will ever work again in this case, and that's not really something that we could use in the industry. Because it's really hard to know will this algorithm in this awesome paper will that actually work in my case. So how can we, from academic perspective, then accommodate such things? So one of the main things is that we want to be more rigorous about how we analyze our proposed methods. We want to be very strict on how we actually conduct those tests. We want to do that on well-known and established benchmarking environments, which is also an apparent problem in real-world robotic learning, because we don't have labs, 100 robots doing some tests. We've seen it with computer vision as well. During the 90s, they also suffered a reproducibility crisis, but like the spark of data sets, also in the late 2000s, like really accelerate that process. So we also want to use proper statistical methods to actually validate our results. And we want to do that because we want to ensure the accuracies. And we can do that both in hyperparameter space and also in data space. What I mean with this is that we could, in theory, we could say that, okay, so I have developed this awesome algorithm. I'm obviously an expert in doing that, but I might not be that good at tuning TRPO or PPO or whatever else so to ensure that it would be fair, I could take all of the algorithms I want to compare it to my colleague and ask him to do it. I could also set a fixed budget for I want to use this amount of data to tune my algorithms. I could also do it in the usage. So then it leads to this case of we actually want to see the cases that failed as well as the one that succeeded. I think we have an inherent problem in robotic research we always claim success. we design our hypothesis around the results that we get. And that's a shame that leads to an acceleration of this very competitive nature. So the predominant factors that affects reproducibility is that we have a lack of access to methodological details, data, and research material. Then we have an inability to manage these complex data sets and environments. We also have very poor research practices, if we even have any research practices and experimental design. And then we have this academic publish or perish culture that we also are addressing in most schools. So it's a lot of work from an academic perspective to ensure that your work is reproducible. There's a lot of tooling, there's a lot of working for this, and that's probably also why we met with the idea that there is a trade-off between rigorous analysis and fast continued progress of science. But let me ask you, do you actually think that there is a trade-off between going nowhere fast and going somewhere else? I don't think so. I think the slow and steady progress would be better off with actually a validated resource. So what are we doing about it at UR? What are I doing about it? So we are continuously advocating reproducible research. We are joining conferences like this, obviously. And then we're also teaching scientific methods within robotic learning. We have a course at the University of Southern Denmark, which is pretty close to our headquarters there. And then we also have a course at the University of Alberta, where we have another professor doing that. Yeah. So we also have components of well-designed experiments. And like during my PhD, I was wondering a lot about why is it that we have the state that we have. And what I found out during my PhD was that we have a diverse background. We are a lot of different people. We are roboticists, we are engineers, we are software engineers, all working in this robot learning domain. And that can become quite a mess because we have different ideas of how experiments are designed, if we even have them. So one of the outcomes of my PhD was stating that we should actually design our experiments before conducting them. And it's pretty basic stuff, right? It's something that we should all learn during our university studies. I'm a roboticist engineer. We weren't taught this. We were just like, okay, go out in the field and play with this and then see what happens. So people will write up a report about that, then everybody's happy to, ooh, that's not really scientific. So this is something that we are really keen about. That's something that we are doing a lot at UR as well. Then there's this dependency, which we ran into a lot. So a very basic tool, I guess that this is pretty common by these days now, is that we should all use stuff. It is so easy just to wrap it all in tail, then we at least ensure that we could run it on some other computer. Good. And we would also argue that designing the machine learning pipeline, so ensuring that the data that flows in actually are matched with the operation that transforms the data into something else, that you have the transparency and through your system. That's something that's pretty valuable, and also especially for making guarantees. So how do we do it at UR? So at UR we have this value, and we say that we continuously redefine automation, and we do that because that's the only reason that we could ever keep that market share of 50%. So we have a series of different horizons we look into. The majority of our research and development teams are looking into Horizon 1, where we do incremental innovation improvements. And that is obviously feature requests, building our product to be have a better user experience, stuff like that. Then we have the next level, Horizon 2, where we encourage all employees across our product creation teams to come up with ideas. So if they have some sort of idea, they could go and pitch it to our senior management. They could get funding, like a startup, and then like pursue this idea that they have. So they would essentially work as a miniature startup within the company, trying to solve this specific user problem that they found, or this awesome feature. Then the next level is Horizon 3, which I am mainly working in, is this disruptive innovation. So this is much more research heavy. This is obviously also why I'm here today, is to get inspired by all of these amazing technological advances and activity. That's more about what's the next leap within automation. We had one in 2005 when Esben and the other two guys like redefined automation through our cohorts, but we're now looking to expand that. It all boils down to Henry Ford. So if he had asked the people what they wanted, then they would have said that they wanted faster process. So this speaks really into how we have been working in UR previously versus how we will do it moving on. So for the last, close to 15 years, it has been very closed R&D at UR. It was so bad that even sales personnel were not allowed into the buildings where R&D was working. We have recently opened that up a lot. Also, one of the reasons that we could stand here today and talk about how we actually work. Because we want to take a much more user-centric approach. So, how do we do user-centric innovation? And the key here is that science is innovation, but innovation is not always science. And we say that because, at least at UR, we don't necessarily need to go out and do 32 customer interviews in order to do some very fancy statistics on exactly that. So how do we actually allow these small sample sizes in industrial integration? We do that at UR by following this lean startup approach. Basically, lean startup works in this loop where you build, measure, and learn. And the important thing here is that we measure by our customer. We go out, visit customers. We don't just sit in our lab, build features. We need them to say what's wrong with our product. And there's a lot of things wrong with our product. We need to fix those in a prioritized way. And we do this by this product discovery. We need to understand what is the complexity, what is the issue that our customers are facing. And not necessarily just ask them, what do you want? Do you want this awesome feature? Because people will just say, yeah, this looks great. Yeah, let me install that and then we'll never use it. Most of our robots deployed in the field are never upgraded. So the new features like built in are only on the robots sold after the software. So what can we learn about that? That's one of the key insights that UR made during the last few years was that, okay, so if people are not upgrading the robots, why is that? Is that because they don't see value in what we are actually creating? So that was the spark of this whole user-centric innovation. We need to go out, understand our customers. Then we need to do some comparisons as well. And there's some formatting that has been, sorry about that. Okay, so one of the other outputs from my PhD was how can we statistically compare results with our validated ones? We have a lot of samples. How can we validate or compare that with single trials that other people report? So what we did was we built a statistically method where we had some empirical data and we fitted 100 theoretical statistical distributions to it in order to find the closest match. So basically it works, the thing that we want to do is figure out, can we actually achieve a mean value that's at least as good as the one reported in the original work. And by following this approach, we can compute those p-values and then do the statistical test to see if our hypothesis about reproducibility is actually good. And this is some of the core work that the university proposes. As a summary, the list of issues that we must deal with from both industry and also academic perspective in order to have scholarships that are complete is that we need data sets. Those need to be available. We need to have the implementation or the executable files in order to run the complete experiment. Also the things that generate the figures of the scholarship. And we need version numbers of dependencies or some sort of containerization. We need an account of all type parameters, how they were obtained. So stating that we just pick them out of the blue air, that's fine. But at least stating how they were obtained so we can all move on. Then there's the segregation about training, testing, and validation. Says that pretty basic stuff in machine learning correlation, but seemingly harder in recombinant. Then we have the specifications of random seeds and the specifications of the computing infrastructure used to obtain those results. So I think that I'm running out of time. I would like to leave you with this conclusion from Untitled Chapter, which states that an article about computational science in a scientific publication is not the scholarship itself, it is merely the advertisement of the scholarship. The actual scholarship is the complete software development environment and the complete set of instructions which generate figures. And I think they said it very well, and that's back in '95. It's a long time. Thank you.
Do you have any questions for our speaker?
Yeah, thanks for the talk. My question is on sort of designing experiments before or after you design the idea. So I think it's sort of pretty common in our industry to have an idea, try to implement it, then come up with a data set, then like machine learning, train on the data set, so on, then see if it actually worked with some experiment. And if it did, then you come up with some reason why it worked. You kind of mentioned that. In other areas like economics, let's say, it's pretty common to do it the other way around. How much of that do you think is due to this being more of a engineering challenge, like you're creating something rather than discovering something? And how much of it do you think is just us being kind of lazy and we should do it the other way anyways?
But we are engineers is inherently lazy, right? So that could be both. But I think you're spot on at that point. We have a lot of other fields where you are forced to come up with a hypothesis that you need to submit before you can actually then a few months later submit your results and then see if they validate or invalidate your hypothesis. The way that we do it with this user-centric approach is that we want to do minimum viable products that are so as minimum as possible. So that could be custom use. So okay, so we have this idea that the user has some issues about not having air through. So that's a hypothesis. Right? We want to go out and test that. We might start out talking to a few customers that then would have the problem or not. We would then escalate that into okay, so maybe we can now invest a little bit more time into this issue, some validation. So we can like do a stage video of how it could work or a prototype, how it could work with area. And this approach just really speaks into this understanding the customer issue. From the academic perspective, I'm not sure that that's the correct approach, but I would argue that we should look more into the fields where they are forced to submit their hypothesis first, especially if you are interested in seeing those cases that fail. So we have more even distribution. I hope that answers it. Thanks.
Okay, I have a somewhat related but slightly different question. So I fully agree with your emphasis on reproducibility. It's very important. But the thing that I always think of is back to when I was a grad student, I was always running from one thing to the next, putting out fires, no time for anything else except for graduating. And so reproducibility, of course, it doesn't get you published, it doesn't get you grant funding. So how do we realign the incentives of academia so that to allow academics to actually focus on reproducibility?
Yeah, that's a very, very good question. And it is one of the things that will always that was also addressed in the previous slides, right, with the field robotics, something that you really don't get a lot of attention or grant money for. I was obviously lucky because I was an industrial PhD. I was employed by a company to do this work, so I've not felt that personally. But it is obviously a very, very huge problem. We need to also have the funds, like raisers or the people granting you money, to also be aware of this issue.
Actually, if you don't mind, I'll have a follow-up for that real quick. So industry is a recipient of wonderful and great research in academia. What can industry do to actually help in reproducibility?
Yeah, that's also a very good question, and I think that's something that we should, from an industrial point of view, also give something back, right? It's all about, so we get a lot of things from academia, and then we keep it because we cannot tell anybody about it because we will ruin our business. It doesn't work like that. We need to go back to the industry and say, okay, or to the academic world, say this is what we need. This is what we need in the future employees that we want out of the universities. This is what we need to know, right? So a more complete feedback is necessary. Obviously the very small companies are in a rush also to put out fires, but when we grow up a little bit larger, then I think it's a responsibility for companies also to go back to academia and finish that or complete that feedback loop.
Thank you. Let's thank our speaker one last time.